Okay, so this is the lesson for Unit 1, Day 2. So we started today with a warm-up. If you weren't in class and you're watching this video, take a moment to copy the warm-up. I would pause the video, try to do the warm-up yourself, and then play to check your answers. So I'm just going to go over the answers here. So the square root of 16, well, that's a perfect square, so I can take the square root of 16, and I know that that's 4. Whoops, looks like I need a pen here, so let me grab that. So I know that that's 4. Now the next one, the square root of 75, that's not a perfect square, so you were taught at some point, well, you need the perfect square, which is 25, and then its factor, which is 3, and the square root of 25 is 5, so my answer is 5 times the square root of 3. Next, well, 27 is a perfect cube, so when you take the cubed root of that perfect cube, you're getting 3, because 3 cubed is 27. So you're taking the cubed root of 3 cubed, and the cube root undoes the cubing, which means 3 is my answer there. Number 2, this is like what we were doing yesterday in class, so it's talking about subset of real numbers. P is describing people who participate in this race. So I want to think about, well, what are my possibilities for numbers of people? Can I have negative people? I don't think so. Can I have decimals for people? Don't think so. Can I have 0 people participating in the race? Well, it's not much of a race if I don't have anybody, but potentially I could have a race and nobody shows up. So 0 is a possibility. 1, yeah, I could have 1 person. Again, not very exciting, but I could have 1 person show up for a race. 2, so forth. But we realize that negatives don't work and decimals and fractions don't work here. So what set of numbers have we just described? We've described the whole numbers. So P is a whole number. Okay. Now, you could probably argue with me that if there are no people, if there are 0 people, then there's no race at all. So if you said natural, I would accept that with that argument because you're kind of right there, but it also makes sense to say that, yeah, we could have a race. It's just nobody showed up, so nobody could race each other, but still we had a race. Just nobody raced. So I would take either whole number or natural numbers there, depending on your thinking of including 0 or not. But anything else really wouldn't work there because you can't have negatives, can't have decimals or fractions. Okay, so that's what we did first. We did that warm-up. Next, we did the timed factoring quiz. So if you were not in class, you'll need to see me to make that up. So that's what we did next. And then after that, we just continued on with our notes. So this is just continuing on in your notebook. We're continuing with Unit 1. And today we talked about simplifying radicals. Hopefully you remember from Algebra 1 that when we have a symbol like this, whether it has a 3 there for the cubed root or 2 or no number at all or a 4 or whatever the number is, that's called a radical. So we're going to simplify radicals. Now what we talk about today should mostly be review from Algebra 1. Maybe we'll look at a little bit more complicated problems than you did in Algebra 1, but for the most part, the concepts should be review. So I'm going to simplify this cubed root of 24 the same way that I did earlier in the warm-up with the square root of 27, or kind of a similar approach at least. So let's, actually it wasn't 27, it was 75. So let's go back to that one. So remember, we're thinking for this one, because it's a square root, the number is a 2, the root is a 2, I'm thinking a perfect square. Well, that was 25, and then 3. Well, 25 is actually 5 squared. And the reason we chose 25 is because it's a perfect square, and I'm taking the square root of it. And then I have 3 left. So when you take a square root of something being squared, the root undoes the power, and we're just left with the 5. And then we have the square root of 3. Well, cube root is very, very similar. The approach is the same, except for rather than wanting a perfect square here, I'm going to want a perfect cube. Because I want to take the cubed root of the number. So you may or may not know the cube root, the cube that goes into 24, or that's a factor of 24. If you don't, then you can start by doing a factor tree to get the prime factorization. And once we have the prime factorization, then we can figure out what the perfect cube is. If you know what the perfect cube is, then you can start with that number. So there's a couple different ways to do it. Let's just say for a moment that you looked at this and realized, well, 8 is a perfect cube. So if you knew that, then you'd have 8 times 3, and that's the cubed root of 2 cubed times 3. And then again, just like I did with the square root, I'm taking the cubed root of something being cubed, so the one undoes the other, and that's just a 2. And then I'm left with the cubed root of 3. Now, that was assuming that I looked at this and immediately thought, okay, well, 8's a perfect cube. And at this point, I'm not expecting you to know that yet. Great if you do, but you don't have to know that yet. So if you didn't know that yet, then we're going to go to a factor tree. So then you wouldn't do quite the same approach. You would do a factor tree next. So I can start with any two numbers I want, just to make it different than what I already did here. I'm going to do 6 and 4. So then I'm going to keep factoring until I have the prime factorization. So next 2 and 2, and here 2 and 3. And all these numbers are prime, so I can't factor that any further. So the prime factorization is 2 cubed times 3. So now I'm ready to put that prime factorization underneath a cubed root. Okay, and now I'm at the exact same point I was when I did it differently. So again, cubed root of 2 cubed, the cube root undoes the cubing, which means just 2. And then I'm left with a 3. Now you don't want to write it like that because that says 2 times the square root of 3. It's the cubed root, so you have to remember that little number there, which by the way is called the index. The root number is called an index. So I have 2 times the cubed root of 3. That is my final answer. Okay, next. Again, if you realize right off the bat that 8 is a perfect cube and it goes into 40, then you can start with 8. I think since we did this tree on the last one, we don't have to necessarily do the tree again to realize that we're going to have 2 cubed, which is 8. So 8 times 5 is a cubed root. So again, 8 is 2 cubed. So I have 2 cubed times 5, and I take the cube root of 2 cubed, that's 2, and I'm left with the cubed root of 5. There we go. If that confused you and you like doing the tree to get the prime factorization, that's fine. You can do the tree. So 4 and 10, 8 and 5, 2 and 20. Doesn't really matter. I'll do 4 and 10. 2 and 2, 2 and 5. So I'm seeing 2 times 2 times 2. That's 2 cubed times 5. So now I'm putting that underneath a cubed root like I just did here, taking the cubed root of something being cubed, so that's 2, and I'm left with the cubed root of 5, so 2 times the cubed root of 5. Okay, moving on. So next thing I had students do was I asked them just to copy this set of notes there. Everything above the line I just drew. So take a moment, pause the video, and copy that so you have that exactly in your notes. Okay, so now that you've done that, let's make some sense of what you just wrote down. So first of all, this is reminding you of a rule that you learned in Algebra 1. The rule taught you how to go from this form, which we call radical form, into this form, which we call exponent form or exponential form. So, and you can go vice versa. You can go back and forth from one form to the other, or starting in exponent form and going and putting it in radical form. So you learned that when you have a number that's in radical form, the way that you put it in exponent form is by making a fractional exponent. And the numerator of the fraction is the exponent of the, this here is called the radicand, the number that's underneath the radical. So the exponent of the radicand, it is the numerator of the fractional exponent. And the root, which I called b here, the root also has a name called the index. The index is the denominator of the fraction for the radical, or for the exponent. So Just remember, the root becomes the denominator, the exponent becomes the numerator, and the base stays the same. And that's how we go back and forth from radical form to exponent form and vice versa, exponent form to radical form. So that's the first thing that you were reminded of. The second thing we'll talk about in a moment is whether the root is odd or even. So we'll get back to that in just a moment. But before we look at that, let's go ahead and try this first problem, and let's apply just the rule itself. So I'm going to change x to the 12th, the cubed root of that, into x to the 12 thirds using that rule. Well, 12 thirds is 4, so I want to leave that as x to the 4th. Now, what we have to do here is we have to look now to see what the root was. It was 3, and 3 is an odd number. So odd number says all I do is apply that rule and I'm done, which means x to the 4th is my answer. Next one, I'm going to apply the rule. So x to the 2 thirds, and that was an odd root, cube root, so I don't need to do anything else. So that is my answer. Now, later in the year in Algebra 2, we'll talk about how to simplify fractional exponents for variables further. But if the fraction doesn't simplify, like 12 thirds simplified, and I want you to say x to the 4th. But if we get something like this, 2 thirds, that's going to be just a repeating decimal. I don't want you to do that. For now, I want you just to leave it as a fractional exponent for the variables. Later in the year, we'll talk about how to simplify that even further. But that's fine for now. All right, so the next one, let's apply the rule. That gives me x to the 6 halves, and hopefully you realize there's no number, so we know that's a square root or 2 index. So 6 halves, which is 3. But now I have to check the root or the index is even. So it says when it's even, you apply that rule, but then you have to put an absolute value around your answer. Okay, so I did that. And now I want you to listen very carefully here, because this gets a little bit tricky. Even though I followed that rule and I put the x to the 3rd inside the absolute value, it actually might not need to be there. And here's what I mean by that. Putting the x to the 3rd inside the absolute value may not affect the output at all. So I have to think about that, whether it would. And to help me figure out whether x to the 3rd being inside the absolute value affect my output, I'm going to just think of some number examples that x could be equal to. So I'm going to make it equal to a positive for a moment. Let's say positive 3. If x equaled positive 3 and I cube that, 3 cubed is 27. Well, 27 being inside the absolute value doesn't really do anything to the output, because the absolute value of a positive number is always positive. Okay, remember what the definition of absolute value is. This is a distance away from 0 on a number line. So the absolute value of 27 is 27. However, what if the number was negative? So let's play around with a negative number here. Let's try negative 3 for x. Well, negative 3, if I cube that, I'm getting negative 27. So now I have negative 27 inside the absolute value, and I'm taking the absolute value of a negative. Well, now the number just changed. The output was affected because that x cubed was inside the absolute value. So what that tells you is that absolute value does make a difference. If the output here inside the absolute value was negative, then applying the absolute value is going to change that final output. So what that tells you is that the absolute value is necessary, and the x cubed has to stay there. Okay, that will hopefully make more sense when we get to the next example. So let's move on. First, I'm going to apply the rule, which says x to the 3 halves, because remember this is the square root. Y to the 8 halves is y to the 4th, and z to the 1 half. And for now, because it's an even root, I'm putting that inside the absolute value. Now I have to decide if it really needs to stay there or not. Is that absolute value affecting the final output or not? So let's look at the y to the 4th, since that's more simple than the fractions. So again, we're going to make, like we did with x, we're going to make y 3. Well, 3 to the 4th is 81. So when I take the absolute value of 81, I'm getting 81. But now let's make y negative 3. Negative 3 to the 4th is still 81. And when I take the absolute value of 81, I still get 81. Okay, so in this case, whether y was positive or negative, it didn't really matter because my output, taking a positive to an even or taking a negative to an even power, I still get a positive output. So that number, 81, being inside the absolute value really wasn't affected by the absolute value at all because we're never going to have a negative output when you have an even exponent. So what that tells us is we don't actually really need the y to the 4th to be inside the absolute value. And in general, if the exponent is even, then you don't need the final answer to be inside the absolute value. And when we're looking at whether it's even or odd, just look at the denominators. So 2 and 4 and 2, they're all even. So even though I initially put them inside the absolute value because of the rule, I just determined the absolute value really didn't do anything. So I'm going to take them out of the absolute value. And that is my final answer. So I'm going to go back a minute and make sure we're understanding when we need the absolute value and when we don't. So if we take an odd root, no absolute value is needed ever. If we take an even root, sometimes you'll need absolute value and other times you will not for your final answer. Initially, you really should apply the rule and initially you would have the absolute value. But it's actually not necessary in the case where the root was even and the final output was even, exponent, no absolute value. But if the root was even and the final output was an odd exponent, that's when you need the absolute value. So you want to keep in your mind, even root, odd exponent, yes for absolute value. Even root, even exponent, no for absolute value. Odd root, no for absolute value. And that's the difference. And hopefully that helps you to understand why we need the absolute value or when we don't. It makes more sense with more practice, so let's do a couple more problems. So let's do the cubed root of 32 x to the 5th y to the 3rd. I first suggest you do the number part first, so we're going to do 32. Well, 32, again, I can either do the prime factorization or I can realize that 8 is a perfect cube. So I want the cubed root of 8 times 4, which means the cubed root of 2 cubed times 4. Or if you wrote that as the cubed root of 2 cubed times 2 squared, that's also fine. So I'm taking a cube root of something being cubed, so that's just 2, and I'm left with the cubed root of, I can either write 2 squared here or 4. I'm just going to write 4. That's the number part of my answer. Now, if that confused you, I'm also going to show the prime factorization way. So 8 and 4, 4 and 2, 2 and 2, 2 and 2. So I'm getting 2 to the 1, 2, 3, 4, 5, 2 to the 5th, and I want the cubed root of that. So I can't take the cubed root of 2 to the 5th, but I can take the cubed root of 2 cubed, because cubing and cube root are opposites. So I changed my problem from 2 to the 5th to 2 to the 3rd, which means I left 2 2's out. So 2 cubed times 2 squared is 2 to the 5th. And now I can just pick up from where I left off. So cube root of 2 cubed is 2, and I'm left with 2 squared or 4, and that's the cubed root of that. So I'm getting 2 times the cube root of 4. Now, variables, I just have x to the 5/3 and y to the 3/3. 3/3 is 1. Now I just have to determine whether or not I need absolute value. Well, I see an odd root, so no absolute value. That's my final answer. Okay. And again, for now, leave your x to the 5/3, leave it as 5/3. Don't try to simplify it further. Next one, 81. Well, that's 9 and 9. Okay, and 9 is 3 and 3. 9 is 3 and 3. So 3 to the 4th power is 81. But I'm trying to take the cubed root. So I don't want 3 to the 4th. I want 3 cubed. And I have 1 3 left. So now I can take the cubed root of 3 cubed, which is 3. And I'm left with the cubed root of 3. There's a lot of 3's in this problem. 3 times the cubed root of 3 is the number part of our answer. Now variables, I have a to the, apply the rule, 5/3, and b to the 12/3. Well, 12/3 is 4. This was an odd root, so no absolute value needed in the problem. Okay. Next. So let's do, I think in most classes I got to this problem. In some I got to that one, and some I didn't. But I'm going to do this one in my notes yet, and then I'm going to stop. And I think tomorrow in class we'll pick up with that square root of 18 problem. So let's go to this one. So I'm going to first apply the rule to the variables, which says 14 halves is 7, and 4 halves is 2. And it's an even root, so I know initially I need absolute value around everything. But I'm remembering the rule that says if it's an even root and the exponent is even, I don't actually need to keep it inside the absolute value. But if it's an even root and the exponent is odd, I do. So I'm going to pull the y squared out. It doesn't need to be inside the absolute value, but the x to the 7th does. And that is my answer. Okay, and we're going to stop there for today. And again, we're going to do some more of these problems tomorrow. So we're going to stop for today. Your homework, check that out on Schoology. Your homework for tonight is page 3. Now, if you want to, you can get a head start on tomorrow night's homework, which is page 4. That's on this topic that we covered today. And again, I'm going to cover that more tomorrow. If you don't feel real comfortable with today's material yet, then you don't have to do page 4, but tonight's homework is page 3. Okay, and again, check out Schoology for more details on the homework.